Right. Hi, my name's Edward Blanch. I'm a tech artist. Well, my background is in tech art, and I've been working for Tin Man Games for like 10 years. I'm also now a sort of a farmer because during COVID I moved into the country and now also look after cows. So I do a lot of things now. So yeah, I've been working for Tin Man for like 10 years now, doing a whole bunch of projects like Warhammer Underworlds Online, Table of Tales, Warlock of Firetop Mountain. I also released my own game called Rogue Singularity. So I've been doing, with the background in art, I've just been slowly shifting into tech more and more with the stuff that I'm doing, right? And so this talk is about visual effects, but it's really about using the data in your visuals broadly. So it's not just limited to visual effects specifically here. It's going to follow a lot of things, you know, where you're using your modeling and your data to create a outcome that isn't just as simple as, you know, this is a blue dot or this is a red dot. Right, so basically, the fundamental of digital art as opposed to a real world or print art is really that all of the information ends up being digitally encoded, which means it's not like an analog encoded piece of information. If I've got paint, I've mixed together two chemicals that are producing a color when under the sun, right? When you're putting all of your data into the computer, it's getting turned into a quantized data set of like little pieces of information that the computer then can reconstruct. So the important takeaway in a lot of the stuff that I'm talking about is, unlike when you're obviously doing when you're doing digital work, a lot of those underlying numbers that are being encoded in order to display your art are actually very fungible and modifiable before you get to the display step. So there are going to be some things that you might have thought were immutable parts of your modeling pipeline that you can actually adjust before you draw it to screen and allow that to get tricks out of that you would otherwise not be able to. So I'm going to be talking basically, the first part of the talk is just me going to be talking about what the underlying data for all of this stuff is. I'm going to try and go through it pretty quickly because I then need to explain how that's relevant. But I'm not going to be able to do that unless you understand the data. Then I'm going to talk a little bit about how engines interpret it, how they display it, the tools that we can use for it, and just a couple of tricks that I've sort of picked up along the way. Right. So basically, the two most common types of data that we're going to be dealing with here are basic 3D model data and basic image data. There are other things like animations and all of this sort of other stuff, but I'm really not going to be focusing on that today because at some point I have to stop adding slides to this. So the most important thing to remember is really what I sort of describe as format hopping. As you move from one format to another, what it does is it changes the way that that's encoded. And so you're constantly going to be gaining and losing different pieces of information as you're transitioning from those formats. So one of the examples that I give up here is even just into format. That's in 3ds Max, the difference between an edit poly and an edit mesh. An edit poly is constantly reconstructing the shape, whereas an edit mesh is keeping the shape the same regardless of alterations that you make to it. And so you get weird discontinuities where it doesn't reconstruct the top face, right? Same thing with like a NURB surface. A NURB surface becomes a shape. It's basically a three-dimensional Bezier curve. It becomes a shape that's defined by control points. It's not defined by like, oh, here is a triangle, here's a triangle, here's a triangle. It says, here is a surface that's mathematically derived from points. That goes for 2D as much as 3D, which is to say that the interpretation of the data that you put into the system is as important as the data you put into the system. So in this case, this is 3 different ways of mathematically deriving a curve from 5 points. And depending on the mathematical derivation, you can get extremely different curves out of that specific setup. And when we're dealing with our art and stuff in programs, that same holds true for 3D as much as it holds true for 2D, as much as it holds true for anything that we're doing. So I'm just going to talk about for 3D models, I'm just going to talk about an OBJ format because it's the dead simplest one, because I'm not going to go into details about the others because they get very complicated and frankly you don't need to know how they work under the hood. But basically what you're looking at in a basic model format is we store the actual vertexes, that is the positions of all the vertices of, let's say, your cube. We store the texture coordinates in the file. We store the vertex normals, that is which direction is our faces facing. Parameter space vertices, which is just other parameters that are associated with the square. We have polygon faces, which basically tells us which 3 points are forming a polygon, so which 3 points are connected as a triangle. OBJ supports splines, it supports some basic material information, object groups, smoothing groups, things like this. So basically what that's doing is it has big lists of points, big lists of normals, and then a bunch of big lists that say this normal is associated with this point, this triangle is associated with these 3 points. So when we pass it into the piece of software, it can reconstruct the cube from the information. Now, obviously, we have XBX, FBX, DAE, STL files, Collada. There are a lot of different formats. FBX is the standard. Don't go too deeply into it. There is an entire SDK if you ever have to go into FBXs, but they are really complicated. I mean, internally, they are something else. And that's why there's an entire SDK on how they operate. And it has APIs and things for how you use it, but if you are rolling your own engine or something, which I'm sure no one here is, there are libraries that you can get to work with it, and I recommend going down that route. Don't try and do anything yourself in there because it will break you. And it's also the reason why, like, I've seen people very unintelligently online complain that they can't, like, oh, why can't I just import a raw FBX at runtime into my game and just display it? And it's like, yeah, because an FBX is huge, and sometimes it can have textures and animations, and it has models, and like the way that it handles scaling and hierarchy means that there's actually the model you want in the environment is just a cube, but then you'll discover if you get the raw data, it's a cube that's in a hierarchy of about 15 other points, and each one is describing a different type of orientation and translation matrix, and it will become very complicated. There are reasons why they do it that way, but it's still not sort of like, it's a somewhat of a complex format. So go check out the SDK if you want to do anything in that area. So once you do that, you then bring your model into, in this case, I'm using Unity and Unreal as an example, you import the model into your software package. What that does is it takes the raw model data from an FBX, from OBJ, however you're doing it, converts it into the own internal format that your engine uses. So it's easy to forget that there's actually a step of format jump that happens on the moment of import where information can be gained and lost, and that's where a lot of these settings are. Unity sometimes feels like it doesn't have this step because Unreal's structure is much more like you have a specific import and you click import and it imports. Unity actually does that too. It just feels like it's not because you can see the actual model in the hierarchy. But when you refresh and re-import, it's doing this same process. So sometimes it can seem like Unity has the raw file, but it actually doesn't. It's still doing a conversion on it into its into format. So you can see in here things like calculate mix space. That's the way tangents are calculated. It's a common formula, but you can also import if you set that up differently. Things like smoothing groups. How are you calculating this? How are normals being updated? Both of them really function very similarly, so it's worth reading into it. So when I talk about data transformation, it's important to remember pre-export, that's what the shape looks like in your software. Model file, I've clicked export. Engine model, I've imported into the engine, and then shader data, I'm rendering it to screen. At each stage, something may be lost or gained, and so that's always why, it's important to make sure you keep your raw files and everything as they go down the chain, because you may have encoded, again, if I have a line and that line is a Bezier curve, and then I export that as a JPEG, it becomes, like blocky squares that are dividing that line, and then I bring it into the engine, and then that turns it into a specific JPEG format, and then I draw it to screen. And I'll be like, well, what's gone wrong here? Why does this line look janky? At some point when I've transformed it from one format to another, I might have lost or added some information that I didn't mean to. So basically, I'm sure people here have had to create images and export things from Photoshop. I'm just going through a couple of bits and pieces. Even though you might think that something like that is like, oh, well, that's for 3D models. Images don't suffer from this problem. They do, absolutely do. So one of the things you might notice is that, like, why is color 255? So it's like if you go RGB, each value is in 255. That's because the underlying data is an 8-bit fixed bit value, 8-bit channel. And that means that it can only store 256 values. So if you then map those values from 0 to 255, you have 256 discrete values. So that's why RGB exists like that. When you go above frequently in Photoshop, that's what an HDR texture is, and that means that you can have more than 255 values or 256 values, and often it will use those extra values for lighting. So they say, once I go above 1, anything that is 2 isn't just white, it's actually literally emitting light. And Photoshop has support for HDR textures that you can export, which means that you can paint in light information and things into your images. So this is what I mean when I start to talk about what is actually existing in your data so you can use it. Same thing it goes here, get real familiar with your channels inside Photoshop because you should be spending more time in them, especially if you want to do interesting techniques in here. And that's because once you're in your software package, you can often access those channels individually. You can think of RGB as 3 black and white images overlaid on each other. That's literally how they used to do color photography. You would put gels over your camera and you would take 3 identical photos with a different gel, and then they would take those 3 black and white images and integrate them together to create the earliest forms of color photography. And really, under the hood, the same thing's happening. And then of course you've got your alpha channel, which is a 4th channel that usually stores transparency. Again, they're just numbers. You can do whatever you want with them. It's also important to understand that even at the most basic level, the way information is encoded in an image is also maybe not what you expect. This is such a common mistake people make all the time, which is not understanding what gamma color space is. Human eyes are specifically designed to be able to see light, not be able to see dark, which means that our perception of light and dark is heavily skewed towards light and not dark. So if I'm painting a gradient, it's going to look like the bottom gradient, a gradient from dark to light in what feels like a smooth thing. If I go into my computer and say, I want to go from 0 to 1 in a completely even across the strip, it turns into the top strip, which does not look like a linear 0 to 1 gradient. And that is because my eyes are perceiving all the light in it way more strongly than the dark. And that's what a gamma correction is. We correct encoded gradients to look like what we expect them to look like, not what a gradient actually is. And when we're dealing with the underlying data from image files, you need things to actually be from 0 to 1, not perception from 0 to 1. Because if I want to slide an object from point 0 to point 1, and I want to do that as an even movement, then if you do this, you won't get an even ramping movement. It will be uneven because it is way more heavily weighted towards the dark end of the spectrum in order to account for the way we visualize things. So most of the important data that you're going to end up dealing with when you do bring stuff into things like Unity and Unreal are basic vertex data in your 3D applications. Vertex is just a point in space. It contains position, the direction the point is pointing in, usually vertex color, and up to 4 or 5 UV channels. UV channels are basically just another piece of positional information, is the easiest way to think about them. So position is XYZ position. UV channel is another series of XYZ positions. Typically, the Z, everything almost always has 4 channels because powers of 2 compute very well on computers. So almost everything will be in a power of 2. So typically UV channels actually have all 4 channels in them. It's typically they don't use the last 2 channels when you're using them for most uses. Like if you're exporting something from Max or Maya or Blender, they don't actually use the final 2 channels. When you do a UV, it just gives you an X and Y coordinate because it'll give you a decent coordinate space for that UV. And you can access all of these values individually. The other thing to remember is the reason why we have triangles and we don't use quads is because a triangle is an unambiguous surface. So in this case, you can see we have a quad. Depending on where we draw the triangle or draw the line that's linking the vertexes, you can way change the direction that a quad bends in. A computer doesn't implicitly know which way the quad is going to bend because it depends on your model. So that's why triangulation ends up so important, but this is also a really good example of what I talk about as format hopping. If you set up your format and it becomes a triangulated mesh, you're going to lose your quads. And we all like really working in quads because from an artist perspective, they're much easier to deal with. You can do loops, you can do all these sort of things. But when you do format hopping, you begin to lose things like what was the original quad shape, and then you have to start using reconstruction algorithms to try and bring those quads back, so it can be very difficult. Frequently, things like FBX and OBJ formats will let you export them as quads, and then you use the software to triangulate on import. This can be fine, but when you get into situations like this, you can get unintentional bends where you didn't expect because the computer will reconstruct the triangles in an unexpected manner. So in many cases, if you're trying to be very precise, especially with UVs, you're going to need to go in and make sure that you've set up your triangulation so it remains absolutely consistent and you're not letting the engine and the format hop decide on how your triangulation is going to work. So that's why we have triangles. All those pieces of information I talked about, like position, UV coordinate, color, the way that it's drawn to screen is that it averages those values between the three vertexes. So if I go, oh, here's this spot on the triangle, and we can see we have one vertex that's blue, one is green, one is red, we basically say, okay, I'm going to average the blue, green, and red value based on my distance from those 3 points. All the data works like that. Same for position, same for UV coordinates, normals, all of that sort of thing. That's how it derives it on a pixel scale. So like, this is what I mean in terms of UV coordinates. So basically what we do is for each pixel in between here, we are looking up into our UV coordinate texture based on the distance it is from the three from the three vertexes with what their individual UV values are. So lighting works in a similar manner. The way lighting works is it uses the normal value of the vertex. So vertexes have a normal value that tells you what direction our surface is facing in. So in this case, when you have a smooth normal, what it does is these 2 points in the middle are sharing a normal value that is pointing at 45 degrees outwards. And then for every pixel between the edge and then another edge, it is averaging those normal values, and that what creates the smooth lighting and the bend as it goes from one to another. When you then apply normal maps, they get applied over the top of that and cause sub-bends on a sub-pixel, again, using the UV coordinates to do that. And so that's how an object knows that it's which direction it's facing. And one of the things that I'm going to explain to you is that is not an immutable fact of your 3D model and can be modified. It's also important to remember that that is just one step of the process at its most low level, raw structure. And so when things are actually lit, usually what we do is they're rendered out to what are buffer textures, and then lighting and post effects and all of this work is done by using the buffer textures in order to reconstruct what the image should look like. So in this case, this would be your albedo, your depth map, and your world normal map. So if I then need to do a lighting calculation, I can say how far away, I can look at this map and say how far away is this object? Okay, that's how far it is from my light. I can say which direction is the object facing in, we look in this map, we get that piece of information, and we say what color is the object, and we point to it and we say it's that color. So that's when you're encoding textures for most of your objects and you think things like albedo, smoothness, normal, all of this sort of stuff, that's what it's writing those colors to, is a series of maps that look like this under the hood. And with most major engines, it's doing a lot of them. Sometimes they'll have directional maps, like blur maps, all kinds of things that are happening, alpha map that are happening under the hood, and they can be very complicated. So your shader editors will be what's interfacing with that. But it is really useful to know. So I just had to blast through that relatively quickly because that's what I'm going to be talking about when I start talking about what the, basically, like, so that's what data is for what art is that we're doing. So how does that help us? How does knowing this help us along in this process? So that data that we're inputting into the system is something that we're encoding, and now that Unity, Unreal, all of these major engines are doing visual effects and shaders much more easily, they're giving access to how we interpret the data that we put into the system. And that's where things become really interesting, because it's really easy to see, it's easy to forget that at the most basic level, what you're passing in is usually just a number between 0 and 1. And even though we're using that number typically to do something specific, there is nothing that stops us using it in completely arbitrary ways. So a simple example here is UV coordinates are a coordinate system that's storing position. It does not have to store texture coordinates at all. In this case, I'm using it to store positional coordinates. I want to say, how high is the character between 0 and 1? Where's the top of my character? Where are the feet of my character? Because when I'm writing my shader, I want to know which part of the model do I want to show first, which do I want to show second. And because I'm encoding the way my UV coordinates look like, in the example I've given you here, I've mapped the internal to a shorter height and the external map to a larger height. So when I run the shader, the internals res in before the externals. In this particular context, the way that I've done it is basically, you can see here, I'm just using a little bit of Unity's basic nodes, but Unreal's is largely the same. We basically take the UV as an input, and we're taking the green channel, because green channel is Y, so height. So in this case, you can't, I don't even think I have a laser pointer. Oh, unfortunate. Anyway, so on our maps of the actual characters, Y is usually up, X is obviously across. So, and then basically what we do is we say, oh yeah, I want to, anything that is below a certain value, above a certain value, I want to clip, and then I just want to move that value up. And then thus we can create, a controllable resing effect in this case. And the thing to remember here is that a UV is just a set of values, right, that we basically encode. So when you go into your shader editor, it's just looking for the input of two values in order to effectively do the lookup. So if we go into those two values and we make alterations to them before we then do the lookup, that's where we can create a lot of really simple effects. So with particles and certain types of visual effects, usually one of the simplest things to do is to just scroll your UV. Easiest thing in the universe. In this case, you can see here, all this code is doing is adding time, which is an input value, into the Y value of our UV. And in this case, here's the texture image I want. I'm taking just a straight strip of geometry and twisting it and making sure that my geometry is unwrapped from 0 to 1 in the direction that I want to move in. And then you do a half turn. And then if you just add time into it, immediately you just get a swishing particle. Then take that mesh, take your shader, take the texture, slam it on a particle system. So the particle system is emitting the mesh with the control texture in it. And then all of a sudden you can create these things branching out. That's a ridiculously simple example I did in about 2 seconds, but you can imagine how you can begin to layer all of these things on top of each other to create things that are more and more advanced. In particle systems, and especially cool visual effects, it can be a real nightmare to control how something is going to move and look, especially when you're doing swoops and spirals and spins, and it will save you about 1,000 hours if you just sit down and say, I'm going to model the spiral and the spin I want, and just animate it across the texture and be done with it. And you can do that all in the shader. And in fact, in the example here, I didn't put it in the code, but I've used the alpha value of the particle, because it's additive, to control an offset, so that they don't all animate together. So they'll all be offset slightly from the animation. So instead of just doing time, I say time plus alpha. And it's just enough difference between each particle that has a different alpha value if you just randomize the alpha values or change the values over time. Another alternative from using time is you could say, hey, I don't want to use time at all. I want to add my 0 to 1 alpha value as an offset, and that would have the same effect of animating it if you did a change color over time node in your graphics node, and then you'd be able to control it. I'm not sure exactly. Unreal lets, with theirs, I think it's Niagara, or they've got a few different systems in there, but they do let you control a lot of stuff like that, where you can just pass like UV data, you can pass vertex colors and all of that sort of stuff straight into your particle mesh and materials. Unity can do the same thing. You just have to pick it up. You choose what data channel you want to use. So one of the biggest things that you will use when you're doing a lot of visual assets that are running primarily on the GPU, but even if you're doing a little bit of coding or doing stuff in Unreal graphs and whatnot, time is a linear value that moves up constantly. Every engine has time. Whenever you animate or do anything, you're animating it against time. So in the case that I gave you at its most simple level, we were just saying add time, and we're relying on the fact that the texture is set to loop. So if my value goes above 1, we've wrapped our texture around. And when you do importing for texture, engines will often let you choose do I want my texture to wrap, do I want it to repeat, or do I want it to clamp, which means that the final pixel will go on forever if you go outside the boundary. So trying to understand how to convert time as a value into a format that you can use effectively, rather than trying to bang your head on it. I know a lot of people don't like math and having to deal with it. So one of the easiest things to do, go online, find a graphing system that works. And there's dozens and hundreds of them. They're so easy to find, so you don't have to keep punching random numbers in. So in this case, our friend is the trigonometric sine value. When you put a value into sine, when you sine a value, it will oscillate between 1 and -1 as a nice smooth curve. That becomes basically the underlying mathematical structure for almost everything that moves in visual effects. At some point is a sine time, right? But that curve initially is not going to be a curve that you like or will necessarily work for you. So what you need to do is then add mathematical operations to turn the curve into something useful. So in this case, going from 1 to -1 is not necessarily going to be useful if you don't want to go that low or that high. So you're like, well, I actually need a value that's smoothly moving between 0 and 1. So a really common thing to do here is you, in this context, you take your value and you times it by 0.5 and you add 1. So because sine goes between -1 to 1, that means that the value difference is 2 from -1 to 1. But you want your value difference to be 1. So what you do is you take it and you say, halve the size, and then I want to add 1 at the end, so that instead of going from -5 to 5, it bumps up, so it goes from 0 to 1. And then you get a nice smooth curve. Then there are transformations that you can do all along, mathematical transformations you can do all along the way, where you can bounce it by absoluting the value. So instead of it going to -1, it just goes to 1 to 0 to 1. And then basically you can begin to punch in different mathematical combinations to change the graph into a shape and a flow that you want in order to get the result that you want. And it's going to be way easier to physically graph it than just start punching willy-nilly random numbers into the system. So this is an example of using sine time in this case. So in order to get the effect of a piece of kelp wafting in underwater, basically what you do is you say, okay, so what I want to do is offset my vertexes. I want the sine of height. Because as we saw when I did in the previous slide, sine of time is creating a -1 to 1. So if I want to offset by sine height, it turns our straight vertex object into a squiggle that approximates what a sine curve would look like. So what we do is we can say then, okay, so that would make it static, it wouldn't move. So then what we want to do is we want to say, hey, I want it to be animating, not just be squiggled. So that's where you just add time straight into the calculation. So you say, I want to add time to my height. And then all my heights are going to be offset. So as time gets added, you'll see the sine curve moving up and it will begin to snake. But then you want to be able to get more control. This is where you begin to use that data that you're able to put into things. So in this case, I say to it, okay, I want it to curve, but I want it to curve less as it goes higher. So then I can say, hey, I want sine time, sine height, but then I want to multiply the offset by an inverse of how high it is. And so I might do that using a UV coordinate, or in this case, I might do it with vertex colors. So I could say, hey, when my vertex color, I want to multiply it just literally by my vertex red color. And what that will do is have the effect of saying, hey, the offset is going to be reduced by the amount of red at this location. So in order to get the leaves to flap, what I've done is actually just taken that sine and turned it 90 degrees. So I've got a 90-degree sine curve then traveling across the leaves. In order to create bends that are greater at the tips than the stems I have painted the vertex colors straight into my plant to say, where it's white, let's bend more. Where it's dark, I don't want to have any horizontal blending. And so then the effect of it is you get bends that look like they're nicely bending as though it were a branch or a tree. So this is what if anything, that's my central thesis, is that like, this is vertex color. You don't have to use it to color anything. You can use it to by hand, tell your visual effect how you want it to operate without having to create hugely complicated shaders. So another important thing here is that because a vertex is just a point and our data is just data, the direction a surface faces in is actually just simply defined by the normal of that surface. Now, this is what it looks like in 3ds Max, but most pieces of 3D modeling software have the ability to edit the normal of your point, which seems odd because you're like, well, if the normal of the surface of this table should be pointing that way because the table is pointing this way, why would I ever want to tell this surface that it's pointing in a different direction? In this case, we do it because what we're creating for our game is already an approximation rather than an exact model. So when you take it to a more conclusive element, if I'm creating a bush or a bunch of bushes by putting flat planes together, those flat planes are lighting according to which direction that flat plane is facing in. So if I bundle a whole bunch of planes together and then have their normals point outwards towards where a sphere would point, and then bundle them together, you can see here, the lighting on my flat planes is going to more closely replicate the lighting of a sphere than the lighting of the flat plane that made it up. That's how they did a lot of the fluffy sort of trees and whatnot in The Witness and things like that. That normal manipulation helps you a lot when you have lots of multifaceted objects. The reason why in real life a tree looks fluffy and fuzzy is because it's made up of thousands and thousands of little leaves, and they are all tiny little planes, but ultimately the aggregate of them creates almost a spherical like object. We don't have the, well, I mean, with nanite and things now, we're starting to get towards those poly budgets, but typically we don't model every leaf. We just want a big plane with a bunch of leaves. And also up here, I just did a quick technique where I was showing the same principle can exist for something like a cloud. Our cloud texture is flat, but we need the cloud to be able to light differently. So what you can do is take a cloud texture, subdivide it into a lot of sub-points so that it's got lots of little normals on it, and then you can tip those normals on your flat plane to face the sort of direction that some of the elements on your cloud texture are facing. So that as your light hits your flat planar surface, the facets of your faked cloud will begin to light up roughly, so it's almost like creating a normal map for a cloud, but you do it in a very generalized manner. And you can do that to create interesting lighting effects where you can create a sense of volumetricness to flat planes that have no volume. It's a little bit trickier with clouds because there's transparency is playing a bigger role that are gonna cause other issues. But in terms of lighting, the lighting on stuff like that works. That includes normal manipulation just for your models. So the reason why when you have two objects and you put them together and you can see clearly a seam and a line between them, that is because there is a normal discontinuity, and that's what a hard and soft edge is if you're modeling in Maya. There's a discontinuity between the normals for two vertexes that are adjacent. So you can see that when the light hits, and I think on the example on the right, when the light hits the flat surface, it's lighting it in one way. When it hits the slightly angled surface that's right next to it, it does it another way. Those two vertexes and the mesh triangle that's there is creating the discontinuity. If you put a little lip around the bottom of your model and point your normals straight upwards to the surface that you need to connect it to, you will get an implicit bevel as the lighting will bend from the normal that you set to be fading perfectly upwards until it gets to the flat side of the surface, which means that if you're modeling, sure, you can interconnect these two models and create that yourself. But if you're creating a dynamically generating object, especially if anybody's done hard poly modeling, you can set it up so that you can just stick that onto a flat surface, and that surface doesn't need to have geometry in order to facilitate the intersection. So you have a flat car body and you want to create pieces that can just be clipped onto it dynamically at runtime. You may, instead of actually sculpting different car bonnets and things that you might have there, you might literally just place your 3D object right on the bonnet with its normals facing towards the bonnet orientation that it would be coming down with. And that will help smooth the lighting discontinuity between between those edges. So it has many more uses than just. So data is art is one direction, but art is also data. So a lot of these same principles operate in the opposite direction. So right now I'm telling you how you can encode your art so that it can be interpreted in interesting ways. That same principle can be facilitated in the other direction. Because we know that a UV coordinate is just a series of 4 numbers from 0 to 1, that means that if we encode those 4 numbers into an image texture, that means that we can create a data texture that can tell us UV coordinates. Now, creating it in Photoshop is dead easy. We create a gradient from 0 to 1 in the red channel, and we do it horizontally because that's the X direction. We create a gradient in the green channel, and we do that vertically because the green channel is the Y direction. And this is where we come back to our old friend, perceptual gradients. You need to make sure that when you create the gradients in Photoshop, you've set that gradient to linear. I think it actually might be called real or something along those lines, but you set your gradient to linear because that actually needs to be a number that goes from 0 to 1. And so what you'll do is you get a texture that looks like this, which I'm sure some of you might recognize because that's what a UV looks like in its most raw state, but now I've turned it into an image texture. So I could take that and just paste it right onto a model in Substance. So now I have a texture that contains a UV texture. And then I create a shader that says, give me that texture, and now use that texture to look up into another texture. And so by stamping UVs on my model, I can then say, hey, here's an icon or an image or a symbol or something that I want to show on my character, and now I can display it on each of the individually splattered surfaces on my master control texture. And that lets us immediately do it like that. So rather than having to have separate geometry that holds it, you can think about very quickly how complexly and interestingly that you could do that. Another thing that you can do is take your UV texture, you can run filters and effects over the top of your UV texture in order to create a distortion using your UV texture. So you take your UV, twirl it, and then look up your texture through your twirled UV, and it will have the effect of twisting the texture that you're reading through the UV channel that you've created for it. An important caveat when you start using data textures. So when I quickly set this up for the talk, it was really easy to be able to find where this is going to start going wrong. There's always a solution, but it's important to remember this because you'll get edge cases. So you see this weird green line right at the edge of my splat. That green line is caused because the texture that I'm exporting and importing is a color texture. And my UV coordinates are green and yellow against a black background. So what does that mean when it starts to blend? It tries to blend comfortably between a black background and my green value. That means we get these little half pixels. You can see them curled here. That half pixel isn't just a random value. Because the half pixel's a bit darker, it means that it thinks its UV coordinate is deeper into the object than at the edge, because that means a real number. And the reason why it does that is all of our blending and mipmaps and filtering is designed for perception, not value. We want to see a good 50% blend as something blends from one color to another. We don't want to see what would be correct, which is you would want this to blend towards the furthest edge of what my texture space would be the quote-unquote way that you would expect a mathematical edge to be. And you're never going to be able to 100% eliminate this because at some point your texture is probably going to be downsampled or upsampled, and this will especially be prevalent if you've got things like mipmaps. Really easy solution though. I want to know which pixels are going wrong, and a dark value is giving me a number that's incorrect. So I want something instead. So what I do is I splat it on top of a blue texture. The reason why I do that is because I'm not using blue. I don't need blue. And so in all of my texture, there should be no blue. And I can, when I go into my shader, I can detect blue and say, hey, if I have blue, there's a problem. I'm blending with blue. I shouldn't be blending with blue. And that means that filtering is starting to occur, and I can say, Flick it away. Don't need it. I don't want it. Or I want to do something special with it. So as soon as you do that and then say, hey, if I've got blue, I don't want it, boom, you can get rid of that. And so that can be a really nice, that's the way you start to think about using color as data. So you want to be able to generate these control textures. So as an artist, you need good ways to author these. Having to paint them by hand into each RGB alpha texture in Photoshop is a pain. And if I ever find a Photoshop associate, I'm going to hold them down and scream to them that I want alpha editing tools that are easier and just work like normal. But, you know, we don't get nice things. So the way to deal with it is you use other third-party programs. I'm assuming most people here are familiar with Substance Painter and Substance Designer. They are great for generating control textures. I cannot do them more. I'm also going to give a shout out to one of my personal old favorites, which is Filter Forge, which is basically you can create node-based Photoshop filters. If you decide that you want it, just keep an eye on it because it goes on sale really, really often. So don't buy it when it's full. Don't ever buy it when it's full price. But I've been using Filter Forge for a couple of years and I love it. But it's just it's more like just Photoshop filters, so it can do image editing. But if you've got Substance Designer, you can do a lot of what Filter Forge does just in Substance Designer. So you don't necessarily need it, but it's just an old personal favorite of mine, and I've used it for a number of years. So the big thing that you want to do with Substance is you want to create user channels. So a user channel is something that's not necessarily something that Substance jumps up and down about. But when you go into the export channels, and you can see it here, it's usually under general properties, just above where you go to stipulate the model you're going to bake. You'll see things like base color, metallic, roughness, normal height. Those are the output maps. In this case, that's a Unity configuration, but these are the normal maps these are the maps that are going to be exported out to your software package that you're going to render in. The little plus in the corner lets you create a new channel that doesn't otherwise exist and has no other purpose to it. And it's called user 0, user 1. I'd love if they'd let me rename it. Haven't worked out how to do that yet. There might be a way. And then you can stipulate what type of texture it is. So you can see in this case, L8 for metallic and L8 for roughness just means it's a black and white texture and you only have to like drag between black and white. So when you've decided what type of data you want your texture to be able to hold, you can then just set it as like, oh, I want it to be sRGB or I want it to be a float texture. Like if you can see here that normal is RGB 16F, that just means it's a higher accuracy. So when we talked about it, it goes above 255. Then you'll see it show up when you're painting and in your material planes, you'll see, hey, we've got user colors, yay. That means that we can now paint with a user color straight into our, onto our model. So if anyone needs, I'm about to jump off this. I've seen a couple people taking photos. I'm sure I'll put the talk up online, but I can jump back at the end if people want to re-see it. So you can see here, that's how I did the splats for the example that I gave there. I created a brush whose color in whose RGB color inside the user channel was the splat map that I was putting on there. And then I put it on blue. Here's another example of where I just really quickly mocked up, hey, I want 3 different types of like patina, and I want them to blend in one after the other. So what I did is created a custom user channel, red, blue, green. They're called, I can't remember what LUDGE is, but it's added. You just want plain additive. That means it will add the red, add the green, add the blue on top of a black base. So you get this weird like multi-colored image that you're seeing there. And what that means is that I will end up with a texture which has this black and white mask in it. It will have that black and white mask in the green channel and that black and white mask in the red channel. And then when I bring it into my software, I just go, hey, I want you to slowly start using the black and white masks to blend to a new color and blend to a new shininess and blend to a new thing. And I go through one after the other. So I say blend from this, blend to this, blend to this. Can be really useful for things because it means that you can be like, oh, hey, I'm going to go into Substance and I'm going to use Substance's rain filter in order to create a mask for grease and patinaing. And then I can export that grease and patina as a mask, and then I can use that in my shader. And when you come to doing it and you want to export it, what you want to do is you want to take the, sorry, I've got little alarms so that I stay on. Sorry, I'm going very fast, I apologize, but I'm coming right up on the time now. So what you want to do then when you export it is you can duplicate an existing export preset. And then what you do is you go up to the top where you see create, gray, RGB, R plus G plus B, RGB plus A. What that means is that that's what you're going to put into that channel. So if you put RGB, it just means you can drag an RGB straight into it. If you want your RGB to come from, say, 3 different, so you could create 3 user channels that were all gray. And then you can say, I want user channel 1's gray channel to go into the R. I want user channel 2's gray channel to go into the B. Then you name it in the same way that you might name another export format. And in this case, you can see that I've put, I think I called it slime color at the time, and the UV stamp as the RGB coming from those user channels. Now when I press export, like a normal map, like a metallic map, it will export my user map with it. And then I can use that as a standard export preset that I have now. If I do it that way, when I set things up and I create my new materials, I immediately have my cool stuff. And the very last thing I will mention is that once you've managed to put those sort of standard things together, I don't think Substance yet has a way to export your presets, which is really, really annoying. But if you open up a file that was set up with the export preset, you will find the preset in the file that you opened up. So in a way, you can just share the file in order to get the preset. So the very last concept to add complexity to all of this, I'm not going to go in it because it's going to take too long, but remember that because all of this is working on image data, if you've got a render texture, you can just pass a render texture in and suddenly everything becomes more complicated, but in a good way. So in this case, I'm throwing in a render texture of a cube into the splat maps that I created on the model, which means that I can have an animating object splattered onto a model, and you can imagine the myriad of ways and things that you could do with doing that sort of thing. In this case, in Unity, it's reasonably easy to set up, and I think it's pretty easy to set up in Unreal too. In this case, all I've done is I've pointed a camera at it, I've said render only the cube, and I've set the background color to be transparent in the alpha channel. So that means the render texture that it creates is going to be an alpha cutout like I would if I was exporting a PNG. And I can just slam it in. And if what you're creating gets really expensive and out of hand, it can sometimes be really useful to just pass it into a render texture and then use the render texture. And if you take your render texture and render it at a lower size, then straight up. So this was a caustic map that I created for a project a while back. It's hella expensive because that's a mathematically generated texture. So what I did is I just went, oh, I need the caustics everywhere. So I did it at 256 or 128 actually, made it blurry and pointed the camera at it and then turned it into a light that was projected everywhere and went, hey, that's much cheaper now. I don't have to calculate per pixel every piece of my caustic calculation. So you can begin to think about how other things that I have done in the past have included we rendered out we experimented with rendering out a character as just their UV coordinates so that we could apply a material to a 2D plane, and that material could have come from a character, and so it would look like a little icon of, say, what my character or customizables was going to look like, but it was just a quad with a material applied. But in the background, I had rendered out the character, all of the character's details in order to render it on the quad, and it could be rendered with different materials without having to re-render the underlying character. So you could render hundreds of characters standing in my menu when really you've rendered out 6 or 7 maps for the one character. And basically doing what the lighting stuff that I was talking about earlier. So yeah, that might be it. I think I'm very close. So is there time for questions or? So sorry if I went a bit fast. I had a little bit to get through, and I think we're almost right. Like I managed to time that out to the minute, I think. So we've got like 1 minute if people have a couple of questions they want to ask, or another slide they want me to go back to.
Or is there somewhere they can find you outside?
I'll probably just be standing right outside after the talk. Oh yeah, sorry. Good point. Yeah, you can find me on Twitter under TechArtEd.